Okay, great. So I'm delighted to introduce our next speaker, Earl Campbell, who will tell us about Riverlane. Please take it away.
Hi, thanks for the introduction, and it's great to be here speaking to people in person. It's my first time in front of a crowd since before the pandemic, and it's also the first time I've done an industry session speech. And today I'm going to be telling you about this lovely company that I've recently joined called Riverlane, and its mission to build an OS for error-corrected quantum computing. So maybe you're wondering what an OS is. And I'll try and say a little bit about that through this presentation. I was told to make a 12-minute presentation. I think I'm probably going to even fall shy of that. So hopefully we'll all be able to finish a little bit early to this session and get on to dinner. And in fact, I probably could have made this talk even shorter, because really all I want to say is encapsulated by this tweet from a few weeks ago, which is that, surprise, surprise, we're hiring. Much like everyone else, we're hiring. But I think one thing I also tried to kind of slip into this tweet without making a big deal out of it was that the company has somewhat pivoted away from thinking about NISQ applications to being much more focused on error correction. So you might have noticed on the title slide, said that we were going to build an OS for a error-corrected quantum computer. And so I guess that's very different from the goal that Ashley set out for Phasecraft and many other companies. I think there's lots of kind of interesting observations you might be able to make. So at the panel session, we had at least 2 speakers who weren't sure exactly whether there would be a quantum advantage that you could get in the NISQ era. So there's been this kind of big NISQ buzz over the last 4 years. But I think where we're landing at the moment is that there's still a lot of uncertainty about where NISQ is going to go. I think if you were to say to someone who wanted to invest like hundreds of millions of pounds or dollars into building a quantum computer, that you wanted to build a quantum computer and you weren't quite sure if it was going to do anything useful, then they probably wouldn't give you the money. But if you think about error-corrected quantum computing, there is a very firm, compelling case that as long as you can get below the threshold and you can deal with some scaling issues, then you will be able to build something that's going to be useful. And of course, you can do some useful NISQ stuff along the way. But at the moment, hardware providers are definitely facing some pain points in terms of things that they struggle with doing on the software side, and they need help with that. And so 3 of the things that the company has really identified that it's pushing on is, well, the first one is build an OS that implements error correction. What this really means is all of the software stack that sits there that goes along with the qubits to help you perform error correction. So most importantly, decoding, and doing various kind of like scheduling and compiling tasks that you need to do fault-tolerant logic. The middle point is about control systems. So this is the software that goes onto, for example, an FPGA that controls the qubits. So lots of noise in the qubits might actually come from the control system, so what they call control noise. And if you're going to be building 1 million physical qubits, you want this control system to be easily scalable and cheap. And then the third bullet point is about algorithms and applications. So trying to develop more algorithms and applications that will help us demonstrate quantum advantage in the kind of error-corrected setting rather than the NISQ setting. So this is a message which I'm conveying to you, that I believe in the company's mission, that we should be trying to solve the major problems that kind of trying to accelerate our progress towards having a large-scale fault-tolerant quantum computer. I think lots of other people agree, lots of people that work at hardware companies. So at QIP in Pasadena just a few weeks back, there was an industry session, and almost every single industry speaker went up and said exactly the same thing in their first 3 slides. Naomi Nicholson came along, and you can't read the small print, but I've copied the main bullet point for you, which is that fault tolerance will be required for commercial applications. Fernando Brandao said error correction will be key to unlocking the value of quantum computing, and it's central to our effort. The Google statement was a little bit more caveated. Their roadmap, their goal, what they're aiming for is to build an error-corrected quantum computer, and they're going to explore NISQ along the way. That makes sense. You're going to have 1,000 qubits because 1,000 qubits is on a way to 1 million qubits. And so you should try and do something useful with them when you have them. But really the long-term goal and the thing that they want to try and solve, I think, is more along the lines of error correction. So this is really hard. So let me just give you a few kind of reasons for why it's really hard. And so this is a slide that comes from a standard pitch deck that Riverlane uses to tell people about what the company does. So most of these slides are silly ones that I put in to do tweets, etc. But this is one that actually comes from the official pitch deck. It's got this statistic on it that you can derive with various assumptions. And it says that for error correction, you have a lot of data. What's the data? You repeatedly measure the qubits. You repeatedly measure the stabilizers of the qubits, and every single time you measure one, you get a bit of data. So say you've got 1 million qubits and you do, okay, yeah, I can't remember the assumptions that went into this exactly, how many qubits there were, but the end result was an estimate that was 100 terabytes per second of data, which is the same as all of the Netflix data globally. That's a lot of data. And you're not just communicating this data, you're decoding it, you're processing it. So it's a huge engineering task to build an infrastructure that will cope with that level of data. You don't just have to believe us that that's the kind of level of data that you have to deal with. This is another QIP. This is Dave Bacon. I seem to have caught him when I hadn't noticed this actually. He's got a bit of a funny expression on his face. This is Dave Bacon giving his plenary talk at QIP. It was a brilliant talk. It kind of highlights lots of what he considers to be specific things that we really need to resolve on the software side to build a large-scale quantum computer. It almost felt like an advert for what we're doing at Riverlane, to be honest. I've just picked out one of the slides where he's talking about the same statistic, and he got the number 3.3 terabytes. I don't know what the assumptions were that went into this, but you get the idea that the ballpark is some number of terabytes per second of data that you have to be decoding in real time. So when I say in real time, what I mean is that you have your qubits, you're measuring them, you're getting data from them. You have to pass this onto some kind of decoder, which should work very fast. And then on the basis of this decoded data, you then have to do something, right? So there'll be some conditional feed-forward logic in your quantum computer. And so then you pass that over to the control system, which then kind of tells the qubits to do something different depending on what the outcome of this decoding was. So this is one of the reasons why Riverlane is working just not on one of these two parts, but both of them together so that we can try and minimize time, not just of one of the components, the response time of this whole loop, okay? And so there's a statement up in the top left that says that the decoding time, or kind of time around this loop, defines the logical clock rate of your quantum computer. So let me explain what I mean by that. So these are kind of space-time diagrams of a lattice surgery protocol for executing a T gate. It's a standard primitive that we use. And so down here, we've got kind of the initial injection or teleportation of the T state. So you've got time going upwards and across a single time slice. Start off with, I've got two different, let's say, surface code patches. The colors indicate, say, the rough and the smooth boundaries of the surface code patch. One in an arbitrary state psi, and one in the T magic state. And you do some merge operation, and after this, you should have executed a T gate. But actually, when you do this merge, you're measuring kind of logical parallel operator between these two patches, and you get some outcome 0 or 1. And depending on which one of those outcomes you get, you either do an S gate or you don't do an S gate. So this is the classical feed-forward aspect of it. But the thing is, actually, it's almost impossible to decode this patch faster so straight away. So there will be some lag time indicated up here. So you've got two different branches, and you've got to decide which branch you're in. But you don't have the data from this earlier point here in order to decide which branch to go into for some delayed amount of time. So you can actually handle that delay by just doing nothing, by just doing the identity. But you don't want to do the identity for a very long time because your quantum computer will be incredibly slow. And so this is what I mean by the logical clock rate is determined by how fast your classical decoder is. I think it's an important point that is not often known. And here's a kind of weird twist, if you'll excuse the pun, on the previous slide. So another gadget that I don't think many people know about is this idea of autocorrect teleportation. So on the previous slide, I was saying if your decoder is maybe not quite as fast as you would like, or has a low response time, a long response time, then you can handle that by just slowing down your quantum computer. But instead of paying that time cost, you can instead pay a space cost. And that's what this gadget does. It comes from various other papers. So you have your state, and it's when you do the T teleportation, you also kind of do an S teleportation in the past, but you can kind of choose to actually execute it or cancel it by measuring either in the X basis or in the Y basis here, where Y basis needs a crazy thing called a twist. So this is a space-time trade-off. There's lots of different trade-offs that one can explore and lots of different ways of doing computation that one can think about to have interesting interactions with problems related to decoder speeds. Yeah, so that was just one little thing I wanted to highlight. So if you are interested in the job at Riverlane, there's a whole bunch of things that we work on. I guess I've kind of focused a little bit on the first bullet point, which is fast decoders, but we're also working on thinking about what the best error correction codes are for different types of hardware. including bespoke solutions for specific types of hardware. What kind of practical error correction protocol, what the best practical error correction protocols, large scale architectural questions. So how do you do lattice surgery on a large scale, for example? And then also the algorithms aspect, error corrected algorithms. So I told you I'll try and keep it short and sweet. If you're interested in a job, come have a look at the website, or you can also email me directly. Any questions?
Any questions? Yeah.
When you say like 100 terabytes per second, could that be that like we end up with fault-tolerant quantum computers and no one wants to use them because they're too expensive to run?
It's definitely a worry, isn't it? So I think Tom kind of alluded to this a little bit earlier. He was talking about if you want to, say, try and use some Grover type algorithm that only has a quadratic speedup, then actually the amount of classical compute you need to go with your quantum computer is so much that you've got to say, hang on, how much, like, could I actually just use that to brute force search through all of the possible like solutions to that optimization problem? So yeah, you have to keep the cost low, which is one of the things I think I was trying to emphasize when I spoke about decoders. The decoders must be something that you can build cheaply, as well as the control systems. Cost is important. That statistic is kind of there intentionally to make you realize how big the engineering challenge is. But there are other large technological things in the world, such as CERN, where they also have a huge amount of data. And in fact, one of our VP for engineering used to work in CERN, and he developed one of the FPGA systems there that's responsible for, well, you get all of this data, but you quickly sift it close to the machine, deciding whether it's relevant data or not. And then if it's relevant data, then you send it off to be stored somewhere else and you look at it later and you do some more analysis. So the more that you kind of move all of your classical compute closer to the qubits and try to reduce the energy consumption, the more like this number of like many tens or hundreds of terabytes seems less intimidating. Like note also that I said that when you do this merge operation for a T-teleportation, I said that you only need like really one bit of information. So the amount of data that actually comes from inside the device off to the control system is much smaller than the amount of data that goes into the decoder.
Any other questions? Yeah.
It's sort of related to that. So, do any like estimates like what that? So when you described a minute ago with certain fixes and basically like throw away some data, have you like got any approximations for like what the actual?
I didn't come up with that 100. That number existed before I joined the company, so don't ask me too many questions about it. But you can see it's going to be a big number, right? How much you need to feed out? It's going to be like many orders of magnitude lower. Like yeah, maybe like 5 orders of magnitude lower.
Yeah.
How's that number with the error rate?
So you're talking about if you pass information on in like a sparse form, or you just list the location of the syndromes rather than passing a string that says there's a syndrome here or not. Yeah, it should go down. But I mean, it's only by a constant multiple, right?
Is it enough that it's actually, is it enough that this is a reason to invest in building
I can't hear you, sorry.
Is that enough to like, you know, is that enough of a gain that it's worth investing in better computers so we get the cost of decoding the service go down?
Yeah, is it worth investing to get better qubits so that you can decrease the cost of doing decoding, rather than just that you can decrease the qubit overhead? I think you've got 2 very good reasons for improving the fidelity there. Yeah, so decoders also run faster when you have a lower error rate.
Given that you want to do all of this decoding as local as possible, are you sort of seriously thinking about trying to get these things actually on the chip with the quantum bits?
I think that's definitely, we're exploring everything.